Hello there, and welcome to Chapter 3, where we're going to look at polynomial and rational functions and their graphs. And you're thinking, well, haven't we studied polynomials before? Well, yeah, you have, but as you notice here, 3.1 is titled Polynomial Functions of Degree Greater Than 2. And so we're going to learn some of the more advanced, if you will, characteristics of polynomials here. We talked in the last lesson about the general form of a polynomial here. They mention some special cases, horizontal lines, lines in general, pardon me, and parabola here. And it says here in this section we'll discuss graphs of polynomial functions of degree greater than 2. All polynomial functions are continuous functions, so we can draw them without picking up the pencil. If f has degree n and all coefficients except a sub n are 0, then f of x is going to look and act like this. And so take a look at 1 and 2. Again, using this result, yes, I know it's in there twice. That's okay. And let's just slide on down here. We've got graphs of a 4th degree, a 6th degree, and an 8th degree. And you're saying, well, you know, Kevin, they look pretty much like the same graph. Yeah, they do. You might notice that there's a little less space here than what there is here. All right, and but what we want to notice in general is what we're going to be studying here over the next few lessons as something called end behavior. All right, I'll throw that term out there. We'll talk more about it as we go. A complete analysis, and again, I know you can read, but I just want to highlight some points here. Since we're doing it this way, a complete analysis of graphs of polynomial functions at degree greater than 2 requires methods that are used in calculus. Notice methods used in calculus here, and we certainly will use them. As the degree increases, the graphs usually become more complicated. That probably makes sense. They always have a smooth appearance, however, with the number of high points and low points, such as P, Q, R, and S in figure 4. Such points are sometimes called turning points, and we call them that because here we're turning from going up to down, going down to up, up to down. So those are turning points. And if we've got an nth degree polynomial, we've got at most n minus 1 turning points. Each function value corresponding to a high or low is called an extremum of the function, and at an extremum f changes from increasing to decreasing or vice versa. We've talked about this in our previous sections. See, we're going uphill from left to right, we're increasing. Now we come downhill from left to right, we decrease, increase, decrease, and increase once again. So uphill, downhill, uphill, down, back up. The intermediate value theorem specifies another important property of polynomial functions, and we're going to build to that. I'm going to let you read through this a little bit here. I'm just going to summarize it. With the theorem itself. If f is a polynomial function and the function evaluated at a is not equal to the function evaluated at b, in other words, these points as you look at them on the graph are not at the same height, they're not equidistant above or below the origin, and a is less than b, so a is to the left of b, then f takes on every value between f of a and f of b in that interval. So in other words, just a real quick here, if this is the point a f of a and this is the point b f of b, somewhere in here, if this is a polynomial function, then all of the y values in this range, in this region, will be hit. Alright, so let's draw a graph and see if we can understand what's being explained here. We just kind of did that. Let's look at example 1 in our notes here. This is problem number 8 from the problem set. It says use the intermediate value theorem to show that f of x equal 2x to the 4th plus 3x minus 2 between a equal negative 2 and b equal negative 1. And so our goal here is to show that this function has a 0 somewhere between negative 2 and negative 1. So let's check this out here. Let's evaluate our function at negative 2. F of negative 2 equals 2 times negative 2 to the 4th plus 3 times negative 2 minus 2. And, well, when we do the calculations here, let's see, negative 2 to the 4th is going to be 16 times 2, 32, minus 6, minus 2. So what do we have here? Well, this is negative 8. 32 minus 8 is going to give me 24. And then f of negative 1, let's see, we've got 2 times negative 1 to the 4th plus 3 times negative 1 minus 2. So this is going to give me negative 1 to the 4th is 1 times 2 is 2 minus 3 minus 2. Negative 5 plus 2 is negative 3. And so since f of f of negative 2 is greater than 0 and f of negative 1 is less than 0, then this means that f of c has to equal 0 for some value of c in the interval, in the closed interval, negative 2 to negative 1. And that shows us how the intermediate value theorem works. Now, if you would kindly work problem 10 for class discussion, and then work 6, 7, and 9 for homework, that would be wonderful. We talked a little bit ago about how we're going to look at polynomials of degree bigger than 2. And so we're going to start out here with what happens when the leading coefficient, remember a sub n is the leading coefficient, and n is the degree of the polynomial. Alright, so when this happens, what we know is this polynomial on the left, that left hand, if you will, is going to be pointed up. We don't know what's going on in the middle, so I'm going to put some little squigglies here in the middle. And we know then also that the right hand is going to be pointing up. Alright, and some examples of this, f of x equal 3x to the 4th minus 17x cubed minus 9. G of x equal 5x to the 6th minus 2x plus 11. So there are some examples where the leading coefficient is positive and the degree of the polynomial is even. Now, anytime you look at a polynomial and that leading coefficient is negative, but the degree is even, so the leading coefficient is negative, the degree is even, here's what we're going to have. This left hand is going to be pointing down, if you will. Something's going on in the middle, and then the right hand is pointing down. So here are some examples of this. F of x equal negative 2x squared plus 5x. G of x equal, negative 20x to the 8th minus 7x to the 5th plus 4x cubed minus 17. Alright, so if the leading coefficient is negative and it's an even degree polynomial, we know what it looks like. So we can say if we've got an even degree polynomial, both hands, both arms of the graph, if you will, are pointing in the same direction, namely positive if that leading coefficient, they're pointing up if that leading coefficient is positive, as we have here, and they're both pointing down if that leading coefficient is negative, as we have here. Alright, and again, we're seeing where the leading coefficient's at. Let's investigate now where the degree of the polynomial is odd and the leading coefficient is negative. In this case, the left hand goes down, we don't know exactly what the middle looks like, and the right hand goes up. So some examples here, f of x equal negative 13x cubed minus 7x plus 10. Maybe g of x is, negative 2x to the 5th plus 6x to the fourth plus 3x squared minus 28x plus 7. We'll be creative there. So again, leading coefficient's positive, and it's an odd degree polynomial. Now let's look at example 4, where my leading coefficient's negative and my degree is odd. In this case, the left hand is going to be going up, something's going on in the middle, and then the right hand is going down. And so a couple instances of this, f of x equal, I don't know, negative 3x cubed, and g of x equal negative 26 x to the 7th minus 10x plus 28. Alright, so guys, as crazy as the polynomials are, doesn't really matter. We can take a look based on what that leading coefficient is and what the degree is. We can take a look and see what that graph's going to look like. And with those facts now in mind, I'll ask you to look at example 12 for class discussion, and then 11, 13, and 14 will go on your homework. Now we're going to sketch some graphs of polynomials, and I know this excites you greatly. I might encourage you to write these polynomials in standard form. You'll notice here in example 2, which is problem 20 from the book, they're trying to mess with us. They're putting this largest term in the back. Yeah, I don't know so much about that. Let's rewrite this as negative x cubed plus 9x. Alright, now if we're going to try to graph this, we're going to need to know where this graph is above and below the x-axis, and in order to do that, we might like to know the zeros. What are the zeros? Well, let's find out, shall we? F of x, let's factor this bad boy. Negative x comes out front, we're left with x squared minus 9. Aha, you say, difference of two squares. Negative x times x plus 3 times x minus 3. Alright, well this sets us up pretty nicely. We've got zeros at negative 3, and at 0, and at 3. Alright, well you'll notice what we've done here. We've just divided this into 1, 2, 3, 4 regions. Alright, 4 regions. And now we'd like to know where this thing's positive and where it's negative. We can get a pretty good idea. I mean, after all, we know that leading coefficient's negative. Alright, and this is odd, so we know that the graph is going to look something, it's negative here, so we know that the graph is going to look something like this, where that left hand's going up, the right hand's going down. And so let's pick some test points here. X equal, let's say, negative 4. What's this give me? Well, the opposite of negative 4 is positive, negative, and negative, which this is going to be greater than 0. And then let's pick, oh, I don't know, negative 1. And so we have a positive here, positive here, and negative here, so this is going to be negative. Alright, let's pick a point in region number 3. Let's go x equal 1. And so let's see, we get a negative, we get a positive here, and we get a negative there. This is going to be greater than 0. And let's look at x equal 5. Alright, well, this is negative, this is positive, and this is positive, negative, positive, positive. We're less than 0, so we're going to be negative here. Guys, we've got a really good idea of what this graph's going to look like. Let's just sketch it out here. We're not going to get real super picky. We know we've got a 0 at negative 3. We know we've got a 0 at 0 and 1 at 3. We've established that fact. We know we're greater than 0 over here, and that better be the case based on the discussion we just had about looking at our leading coefficient and that highest power of x, the degree of the polynomial. We know that we are going to dip down here, and then it becomes positive again at 0, and then it becomes negative again to the right of 3. And so we can get a pretty decent sketch. That's all I'm looking for. Certainly we could pick some more points and we could find actual values, but right now we're just sketching the graph. We're not drawing it in exactly. Alright, we're just picking some test points out here. And certainly, guys, we've talked about this in class before. I'll mention again, if you have questions, please, please, please write them down. Write them down now, and make sure you ask me about them in class when we get to that point. Notice something here, and we're going to be coming back to this in later sections, but notice how I cross through the x-axis, I cross through the x-axis, and again I cross through the x-axis, and I'm going to ask you to note that this is raised to the first power, this is raised to the first power, and this is raised to the first power. Just going to ask you to make note of that right now. We'll come back to it later, but just doing a little previewing, a little foreshadowing, giving you something to look forward to as we move ahead here. Alright, you ready for another? And let's check this bad boy out. Example 3, which is problem 22 from the set here. Find all values where x is greater than 0, less than 0, and then we're going to sketch the graph. Well, first thing we notice, leading coefficient is positive, a sub n is greater than 0, n is even. So we know that our graph is going to look something like this. And so I'm going to go ahead and factor out an x squared here. It leaves me with x squared plus 3x minus 4. We know how this factors. X squared, x, plus 4, and x minus 1. So we'll note that we'll find our zeros. And so what we have something at 0. We have a 0 at 0. We have a 0 at negative 4. We also have a 0 at 1. Alright, so let's check things out here. Let's check things out here. We've got 1, 2, 3, 4 regions that we need to look into. Let's pick our test points. X equal negative 5. Negative 5 squared, that's a positive. Negative 5 plus 4 is negative. Negative 5 minus 1 is negative. So this is positive. We've got x equal, I don't know, negative 2. Pick something in there between negative 4 and 0, whatever you're feeling like. Negative 2 squared, that's positive. Negative 2 plus 4, that's positive. Negative 2 minus 1, that's negative. Two positives and a negative multiplied together give me a negative value. Let's take a look at something between 0 and 1. Uh-oh, there comes the 8-letter F word, fraction, but we're in college algebra, we can handle it. We've got to pick a fraction if we're going to get a number between 0 and 1. We'll go with 1/2. Can't get much more in the middle than that. 1/2 squared is positive. 1/2 plus 4 is positive, and 1/2 minus 1 is negative. Notice here, folks, yes, we really are negative. Tuck that away in your back pocket. I'm going to talk about that a little bit more in a minute. And then let's go to region 4 here. We'll pick a test point, maybe x equal 2. So let's see, 2 squared is positive. 2 plus 4 is positive. 2 minus 1, positive. 3 positives multiplied together, that gives me something that's positive. Alright, so let's take the information that we're given and let's prepare to make a graph, shall we? Here's negative 4. Here's 1. Now, I want you to notice something. We know that this left hand needs to be going up. We know that between negative 4 and 0, we're negative. We know at x equals 0, we know our y value is 0. But look at what we found out. We found out that between 0 and 1, this graph is negative. Alright, and then we know that when we get to be to the right of 1, we know the y values are positive. So our graph looks something like this. I'm going to ask you to notice something here. This is an x squared, x plus 4 to the first, x minus 1 to the first. You're going to notice x squared. My 0 here is 0. Notice how when we get to 0, we kind of bounce off the x-axis. We come up and we bounce back off. And yet notice at negative 4 and at 1, we cross over that x-axis. Again, that little discussion is going to come up later here in the unit. Alright, so if you have questions about that, again, please make note of them. Please make note of them. Okay, looking here at example 4, we're doing the same thing. I want to note, first of all, before we get ready to simplify this, that a sub n is negative, and n is 4. Alright, a sub n is negative, and n is 4, so let's see what we've got here. Now, I can't really do too much. Alright, I can factor a negative out, but that leaves me with x to the 4th plus 12x squared minus 27. Now, one thing you might notice here, if we play our cards correctly, and forgive me, we take a negative out, that needs to be a positive right there. We play our cards right here, we'll notice that when we take that negative out, this changes this sign right here so that it's a negative. So let's make sure we're okay with the factoring. I take a negative off of the negative x to the fourth. That gives me a positive. Positive 12 divided by negative 1 is negative, and then negative 27 divided by a negative, that's a positive. Alright? Now I can factor this. This is going to be x squared minus 9, x squared minus 3. Alright? You guys are saying, whoa, wait a minute. Well, folks, think about this. Okay, u squared minus 12u plus 27, we know is u minus 9, u minus 3. We've got the same thing here, only it's x squared. And then this will factor even more, x plus 3, x minus 3. And here's one for you. X squared minus 3, that's the difference of squares as well. X plus the square root of 3 and x minus the square root of 3. How about that? Square root plus square root minus square root. Alright, so we're taking a look here at what we're doing. And we've got 4 zeros. Let's go ahead and plot them. We've got 1 at negative 3, 1 at negative root 3. Keep in mind that's about negative 1.73. We've got 1 at root 3, and we've got 1 at 3. Okay, this gives me 1, 2, 3, 4, 5 regions. And let me point something out here. We said that the leading coefficient is negative, n is 4. Here's what we're looking for. Okay, both arms of the graph need to be pointing down, something going on in the middle. So let's pick our test points and let's try to get some that'll be relatively easy to work with. For region 1, I'm going to go with x equal negative 4. Alright, so here we go. Now we've got a negative in front of all of these. Okay, I've got this negative here. Let me highlight that so that we don't lose it. There we are. We don't want to lose that. Now, I put negative 4 in, that's negative. Negative 4 in, that's negative. Negative 4 in, negative, and negative 4 in, negative. 1, 2, 3, 4, 5 negatives multiplied together. We know that region of the graph is going to be negative. I told you that negative root 3 is approximately negative 1.73. Well, so let's go with something between negative 3 and negative 1.73. How about good old x equal negative 2? There's that negative in the yellow. Negative 2 plus 3, that's a positive number. Negative 2 minus 3 is a negative number. Negative 2 plus root 3, that's a negative number. And negative 2 minus root 3, that's a negative number. So let's see what we've got here. 4 negatives and a positive. Yep, that's positive. Good news there. Let's take a look at region 3. That's coming between negative 1.73 and 1.73. How about our friend x equals 0? We've got the negative in front. Now I'm going to put 0 in. 0 plus 3, that's positive. 0 minus 3 is negative. 0 plus root 3 is positive, and 0 minus root 3, that's negative. 3 negatives multiplied together times 2 positives, that's going to give me a negative result. And then we look here at 4. Well, let's see. We've got x equal, I don't know, how about x equal 2? We know we've got the negative in front. 2 plus 3, that's a positive. 2 minus 3 is a negative. 2 plus root 3 is a positive, and 2 minus root 3, that is a negative. So let's see here. 4 negatives times 2 positives, that's going to be greater than 0. Now remember, guys, we need this right arm to go down, so we're hoping here that we get a negative result. Let's check it out. I don't know, let's pick x equal 4. How about it? We've got this negative in front. 4 plus 3, that's positive. 4 minus 3, that's positive. 4 plus root 3, that's positive. And 4 minus root 3, that's positive. Alright, I feel like I left one out here. Let's see, the negative in front. 4 plus 3 is positive, 4 minus 3 is positive, 4 plus root 3 is positive, and 4 minus, okay. We're positive all the way around. This is good, less than 0. And there we go. So we're going to sketch in our graph here. Here's negative 3, negative root 3, 0, root 3, and 3. Alright, and so we notice we're going down here, we're above, we're below, and we're below in that entire region. I apologize, 0 is not a 0 here. X equals 0 is not a 0. So we stay below the whole time, then from root 3 to 3, we come back above, and then down below. Okay, so here's our polynomial here, and our end behavior is as to be expected. Now, let's take a look at example 5 here just for a moment. When we look at example 5, okay, we can see the zeros. We can identify the zeros fairly well, I think. We've got one at 1. We've got one at negative 2. We've got one at 7. We have one at 4. And so here we go. Alright. Now let's see. Can we figure out what's going to go on here? Well, if we think about this, let's figure out what degree we have. We can actually take these exponents and add them up. 3 plus 3 is 6, plus 4 is 10. So n equals 10, which is even. And we notice we're going to have an x multiplied all the way through. So a sub 10 is going to be 1, which is greater than 0. So our graph better looks something like this when we're done. Let's see what happens, shall we? We've got our test regions to consider here. 1, 2, 3, 4, 5 of them. And so if x equals negative 3, alright, let's see here. We put negative 3 in. Negative 3 minus 1, that's negative. You raise that to the odd power. Negative 3 plus 2 squared, that's going to be a positive. Negative 3 minus 7, that's a negative, and you cube a negative, you get a negative. Negative 3 minus 4, that's a negative, and you raise a negative to 4th power, you get a positive. So here, to the left of negative 2, our graph is positive. And then let's go between negative 2 and 1. Well, how about our friend 0? Alright, I put 0 in here. 0 minus 1 is negative. 0 plus 2 squared is positive. 0 minus 7, that's a negative cube, that's negative. 0 minus 4, that's a negative to the 4th power, that's positive. And so let's see what we've got. We've got a positive result again. Let's take a look now maybe at, I don't know, 2 perhaps. 2 is between 1 and 4. X equal 2. Alright, so let's see. 2 minus 1 is positive. 2 plus 2 squared is positive. 2 minus 7 cubed, well that's a negative cubed is negative. 2 minus 4, that's a negative. We're going to raise that to the 4th power. And so that's positive. And we get a negative result here. We get a negative result here. Let's check out a number between 4 and 7. I don't know, maybe x equal 5. 5 minus 1 is positive to the 1st power is positive. 5 plus 2, that's positive. You square that, that's positive. 5 minus 7, well that's negative. You cube that, we get a negative result there. 5 minus 4 is positive. You raise that to the 4th power. So here we get a negative result. And then let's go for x equal 8. Alright, let's see. 8 minus 1, that's positive. 8 plus 2, that's positive. You square positive, you get a positive. 8 minus 7 is positive. You cube that, you get a positive. And then 8 minus 4, that's positive. And so we're positive all the way around, and this is good. Both of our arms are going to be pointed up. Now, let's sketch this in here. Here's negative 2, here's 1, here's 4, and here's 7. All right, let me draw in our zeros. Draw in our zeros. So this is going to go up. This is going to go up. Notice here that between negative 2 and 1, we're still above. Then we dip below. You know what? That's a 1, isn't it? My apologies. Let's fix this here. We certainly do not want 1 being to the left of the x-axis. That would not be good. So let's fix that here. Here we go. Alrighty. We said between negative 2 and 1 we are positive. There we are. And then from 1 to 4, notice we're negative. And then from 4 to 7, well, we're negative once again. And then from 7 to infinity, we're positive. Now, I want you to note something here. Note how at x equal negative 2, f bounces. Same way with x equal 4. F bounces again. Alright, it hits negative 2 and goes boing right back up. It hits x equal 4 there and boing right back down. So we talk about the functions bouncing here. Alright, and so for class discussion, I'm going to ask you to work 24 and 30, and then here you go, folks. You'll get a little bit of a workout with that list of problems, but it'll be good practice. It'll be good practice. Alright, and of course, what would a section be without a word problem to wrap us up, huh? Just wouldn't be right if we didn't have that word problem there. Let's see what's happening here. And it says, be careful to consider what a reasonable domain would be for any function that we find. Well, we got a frame for a shipping crate. It's to be constructed from 24 feet of 2x2 lumber. If the crate is to have square ends of side x feet, express the outer volume of the crate as a function of x, which is they want us to disregard the thickness of the lumber. Well, so let's see what's going on here. We've got 1, 2, 3, 4 x's here. 1, 2, 3, 4, and we've got 1, 2, 3, 4 x's here. So we've got 8 x's. We've got 1, 2, 3, 4 y's. And let's see. That adds up to 24 because that's all the lumber that we have. And so our job is to express the volume of this thing. Alright, now remember guys, the volume is length times width times height. And we want to do this all in terms of x. So I need to find y in terms of x first of all. So 4y equals negative 8x plus 24. Y equals negative 2x plus 6. Alright, and we know volume. Volume equals, I don't know how we want to say this, but I've got a length, which is negative 2x plus 6. I've got a width, which is x. I've got a height, which is x. This gives me negative 2x cubed plus 6x squared for my volume in terms of x. Alrighty. And so now let's think about what a reasonable domain would be here. One thing we got to do, folks, obviously x has to be greater than 0. But you know what? So does y. Y has to be greater than 0. And you say, well, okay, but what's that mean? Well, we know that y is negative 2x plus 6. That's got to be greater than 0. So negative 2x is greater than negative 6, meaning x is less than 3. Well, we said here x has to be greater than 0. X has to be less than 3. So we know our reasonable domain reasonable domain is between 0 and 3. Okay. And so we can get ready to draw this, and we could we could test this out and see what's going on here. They want us to sketch a graph of this. Well, let's think about it. I've got zeros at 0 and 3. So let's just pick a test point in here. I don't know. We've got one region that we really care about. Let's let x equal 1, perhaps. And so when x is 1, keeping in mind we're looking at negative 2x plus 6 times x. Well, if x is 1, this is positive, this is positive, this is positive. We're positive within here. And so my reasonable domain, 1, 2, 3. Here we go. Here's our graph. Alrighty. And so now you are ready to go to town on 3.1. Of course, bring any questions that you have with you to class.